Hello everyone. In this lecture, I would like to explain about Clipper circuit as a nonlinear wave shaping. The nonlinear wave shaping is a process of altering the wave shape of a sinusoidal signal by passing through a nonlinear networks. So basically the nonlinear networks are constructed with help of a nonlinear elements like diode, transistors, etc. So when you are passing our sinusoidal signal through these nonlinear networks, the output what we are obtaining is a non-sinusoidal output. So examples for this nonlinear wave shaping are clippers and clampers. So in this lecture I would like to explain about clipper circuits. Clipping means removing or cutting a part. So when you are eliminating some part of our signal, it can be considered as a clipping. So the clippers are the circuits which are used to remove unwanted portion of the signal and transmits only the desired part of the signal. That means when you are passing a sinusoidal signal through a network, so the portion which is not required or not desired for our application can be eliminated by using these circuits. So usually these clipper circuits are helpful where we want to alter the wave shape or when you want to remove the noise over a transmitted signal. That means when you are transmitting our signal due to the external influences, some noise is included in the message signal. So if you want to obtain the actual message, then we need to eliminate our noise. So that noise can be eliminated or the unwanted portion of the signal can be eliminated by using our clipper circuits. So as we are eliminating the signal, so the output signal voltage is limited to certain point. Due to that, the clipper circuits can also be referred as voltage limiters. Or when you are eliminating some portion of our signal, the output or the desired output what you are getting will be defined by amplitude. So as we are limited the amplitude of the signal, then these circuits can also be called it as amplitude selectors or slicers. So generally the clipper circuits are configured in various types based on the elements what we are using or number of components what we are using. According to that we are configuring our clipping circuits. So if we are constructing our circuit with a combination of diode, resistor, reference voltage in a series combination, that can be considered as one of the configuration of our clipping circuit. If suppose we are constructing our circuit with a multiple diodes, resistors and reference voltages, so it can be considered as another configuration. or if you are using your transistor as a nonlinear element in the circuit, then it can also be considered as one of the configuration. Or when you are using two emitter coupled transistors operating as a differential amplifiers, that can also be considered as one of the configuration or one type of our clipping circuits. So these are the general or basic configurations what we can represent for a clipping circuits. So when you are constructing our clipping circuit, the nonlinear element what we are using, according to that, our clipper circuits can be represented as a diode clippers or it may be a transistor clippers. So first we will discuss about our diode clippers. So your diode clippers can classified in various ways like shunt clippers, series clippers, clipping at two independent levels. So these classifications will be based on the how we are going to place our diode in a network or how many number of diodes we are using in our circuit. So if you observe the first one, that is shunt clippers. So in shunt clippers, the diode is placed in parallel with the output. So when you are placing your diode in shunt with the output what we are eliminating, so based on the reference potential, how we are going to eliminate our output. According to that, our clipper can be represented as a shunt clipper above reference level or shunt clipping below reference level. So when you are eliminating our output above the reference potential, then it can be considered as a clipping above the reference level, and when you are eliminating signal below the reference level, it can be represented as a clipping below reference level. Similar to this, in series clippers also we are having clipping above reference level and clipping below reference level. In series clippers, the nonlinear element diode can be placed in series with our output parameter or in series with the output. And another type of diode clipper is a clipping at two independent levels. So in shunt clippers and series clippers, we are going to use one diode to eliminate our signal at one level. Whereas in the clipping at two independent levels, we are going to eliminate our signals at two different levels. So if you want to eliminate our signal at two different levels, then we need to use multiple diodes. So our clipping at two independent levels can also be considered as a double-ended clippers, because we are going to use multiple clippers to eliminate our signal at independent levels. So first we'll start with our shunt clippers. So if you observe our circuit diagram, this is the shunt clipper with a reference potential. For this circuit, if you are applying a sinusoidal signal as an input, based on the input potential, our diode may be under the forward bias or it may be the reverse bias. So in general, for any PN junction diode, if the anode potential is greater than the cathode potential, the diode will be under the forward bias, and if the anode potential is less than cathode potential, diode will be under reverse bias. So when the diode is under forward bias, it can act as a short circuit. So when our diode is acting as a short circuit, you can say the forward resistance of the diode is 0. And when the diode is under reverse bias, it can act as an open circuit. So when the diode is acting as open circuit, the reverse resistance can be considered as infinite 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 resistance. So under the ideal conditions, we can say our Rf equal to 0, that is the forward resistance of our diode is 0, reverse resistance is infinity, and cut-in voltage of our diode as 0. So these are the ideal ideal diode representations. In practical case, these values may be changed. The cut-in voltage of the diode may be considered as some value based on the diode what we are choosing, or based on the diode you may have the forward resistance as well as some larger value of reverse resistance also. Now according to this, so when our input Vi is less than of our reference potential, then you can say our anode potential is less than the cathode potential, so our diode will be under reverse bias. So when the diode is reverse bias, it can act as an open circuit. So the input what we are indicating, or the input what we are representing, the entire input will represent at our output, because our diode is acting as open circuit, so we cannot pass our signal through the diode. So entire input will be represented our output. That means when the Vi is less than Vr, we are getting our output V not equal to Vi. And if suppose if you are representing Vi is greater than Vr, that means the input potential is greater than the reference voltage, then our anode potential is greater than the cathode potential, then our diode will be under the forward bias case. When the diode is forward biased, it can act as a short circuit. So when the diode is acting as a short circuit, the reference potential what we are having, that itself represent across our output. So we can say when the Vi is greater than Vr, V not equal to Vr. So if you observe our output waveform, when the input is less than Vr, our output is same as our input. There is no change in the wave shape. The entire input will be represented our output for the condition of Vi less than Vr. But when we are represented the input potential greater than Vr reference potential, so we are getting our output with a constant potential of Vr, and above the Vr, whatever the input we may have, that entire signal will be eliminated, or the entire signal will be clipped. So if you are observe the output waveform, you can clearly identify the clipped portion of our signal. So the dotted portion of our signal what we are having, the sinusoidal signal, the positive peak what we are represented with the dotted line, that we can represent as a clipped portion of our signal. And whereas the dark line what we are drawn for a sinusoidal signal, that you can consider as your output for a given input. And similarly, if you observe the transfer characteristics, these characteristics which we plot, input versus output, the input voltage versus output voltage. So according to that graph, if you are observe, when our Vi is less than Vr, so our output is same as input. So we are represented that one with a transmission region with a slope 1, and during this phase our D, that is diode, is in off condition, reverse biased. So when the Vi is greater than Vr, we are maintaining our output as a constant with the reference potential VR, and that region we are indicating as a clipping region, and during that phase our diode is in on condition, or it can say as forward biased. Now similar to this, if you are interchange the diode direction and the reference potential direction will be anything, either plus VR or can say minus VR. Then according to the diode direction and reference potential, either we may clip our signal above the reference or it may be the below the reference based on the diode position what we are having. So this is about our shunt clipper. Similarly, if you are observe our series clippers, you can clearly observe the structure difference between this shunt clipper and series clipper. In shunt clipper, we are placing our diode in shunt with the output. In series clipper, we are placing our diode in series with the output. Now if you observe this circuit, when we are applying our input Vi is less than our reference potential, then the condition what we will obtain is anode potential is greater than the cathode potential. So our diode is under the forward bias. So when the diode is forward bias, our V0 is equivalent to our input Vi. It means when Vi is less than of our VR, we are getting V0 equal to Vi. And if our Vi is greater than of reference potential, Vi greater than of VR, so diode will be under the reverse bias, and VR itself represent across our output. So V0 equal to VR. So if you observe our output waveform, below the reference potential, we are getting the complete input. So V0 equal to Vi when Vi is less than of VR. But when the Vi is greater than of our VR, we are maintaining our output with a constant potential of VR. So we are removing the signal above the reference potential. The same thing you can observe in the transfer characteristics also. During diode on, we are obtaining output in the transmission region. When the diode is off, we are getting output in a clipping region. So this is about our series clipper. Similar to the shunt clippers, in diode clip series clippers also, we can change the diode direction as well as we can change our reference potential. Either it may be plus VR or it may be minus VR. According to the diode direction and reference potential, we can eliminate our signal or we can remove our signal above the reference point or it may be below the reference point. And the other representation of our diode clippers is clipping at two independent levels. In clipping at two independent levels, we are going to use multiple diodes. These multiple diodes are useful to eliminate our signal at different levels. So according to the circuit, if you are observe, when the input Vi is less than or for VR2, which is connected across the anode terminal of our D2 diode. So when the Vi is less than or for VR2, the anode potential of our D2 diode is greater than the cathode potential of the D2 diode. So D2 diode is in conducting then that means our D2 diode is under the forward bias, so it can act as a short circuit. Coming to the D1 diode, as our Vi is less than of our Vr2, which is a negative potential, that means anode potential is less than of our cathode potential, because our cathode of D1 diode is connected to plus Vr1, positive Vr1. Then in that case our D1 diode is under reverse bias, it can act as an open circuit, and D2 is forward bias, it can act as a short circuit. So when D2 is acting as a short circuit, the Vr2 reference what we are having, that itself represent across our output. So you can say V0 equal to minus Vr2. And when our input Vi lies in between minus Vr2 plus Vr1, so during that phase both the diodes are under reverse bias, D1 as well as D2, because for both the diodes the anode potentials are less than the cathode potentials, so both the diodes will be under reverse bias and both will be act as a open circuit. Then the output what we are getting is same as our input, V0 equal to Vi. And in the third case, when you are providing Vi, input potential is greater than of our Vr1. In this case our D2 is reverse bias because the anode potential is less than the cathode potential, and D1 is under forward bias because the input is more than our reference Vr1 potential. Then D1 will be under the forward bias, so it can act as a short circuit. So when the D1 is acting as a short circuit, the Vr1 reference what we are having, that itself represent across our output, so you can say V0 equal to Vr1. So if you observe our output waveform, we are passing our input signal in between Vr1 to Vr2. So if our input is in the range of Vr1 to Vr2, we can obtain our output V0 equal to Vi. But when our input is above the Vr1 or it may be below the Vr2, so we are going to remove that particular portion of our signal. So as we are eliminating our signal at two different levels, above Vr1 and below Vr2, then this circuit can be considered as a clipping at two independent levels, or it may be a double-ended clipper where we are removing our signal at two ends. So if you observe the transfer characteristics of the circuit, below Vr2, that means when Vi is less than of minus Vr2, D1 off and D2 is on, so we are getting our output with a constant potential of Vr2 and the slope will be 0. So if our input is in the range of minus Vr2 to Vr1, output is same as our input, so with a slope 1, and our D1 as well as D2 will be both in off state, so that you can represent as a transmission. And when our input greater than of our Vr1, then D1 is in on and D2 is off state, so again we are in the clipping region where we are removing our signal above the reference point, and with that will be indicated with a slope equal to 0. Now based on this concept, if you are observe the example, here we are represented the transfer characteristics of two circuits, and above the circuit transfer characteristics represented for a clipping at two independent levels, double-ended clipper circuits. So in first case, we are clipping our signal at 5 volts and 8 volts. That means below 5 volts we are clipping our signal. So if you are applied a sinusoidal signal below 5 volts of input, positive cycle or negative cycle, that thing will be eliminated, and above 8 volts it will also be eliminated. So we are getting our signal between 5 to 8 volts. So that will be treated as a transmission region. Below 5 volts clipping region, above 8 volts clipping region. So similar to the other transfer characteristics also, can observe we are clipping our signal at two independent levels. Right? Hope you understand the concept of a clipper circuits. So these are the some basic idea of clipper circuits. Thank you.